Alright, in this video we study what distinguishes the set of real numbers from the set of rational numbers. That is the continuity. So we study the continuity of real numbers, and in particular we prove Archimedes' principle as a consequence of the continuity. Okay, let's start. So, continuity is rather hard to grasp rigorously. So we need a bunch of new ideas. And the first thing we define here is upper bound and lower bound of a set. Upper or lower bound. Bound. Okay. So suppose S is a set of real numbers, subset of real numbers, and alpha is a real number. First, we say alpha is an upper bound of S. So this means, by definition, for any element x in the set S, we have x is less than or equal to alpha. So if we visualize this, let's say this is the number line and this is the set S. Okay, so any element alpha that is greater than or equal to all of the elements of S is called an upper bound. So for example, this can be an upper bound. Oh, this can be upper bound. This can be an upper bound, but this is not an upper bound. This is not an upper bound because there are some elements of S that are greater than alpha, greater than that value. So any element above the interval S is an upper bound of S. And next is a lower bound, and we say alpha is a lower bound of S. So that means for all elements x in S, x is greater than or equal to alpha. So it's just opposite of upper bound. So suppose this is S, then this can be a lower bound, but this part cannot be a lower bound. Okay, this is not a lower bound because there are some elements that are less than this value. So anything that comes below this subset S can be a lower bound. Okay, let's see a few concrete examples. Suppose we have this set A that is a subset of real numbers that are let's say less than or equal to 1. Okay, so for this set A, any real number that is greater than or equal to 1 is an upper bound. For example, 2 is an upper bound, 1.5 is an upper bound, 1.11101 is an upper bound, and actually exactly 1 is an upper bound, because all of these numbers are greater than or equal to the largest value of the largest number in this subset. And another example, let's say set B is a subset of rational numbers that are greater than square root of 2. Okay, so in this case, any real number that is less than or equal to square root of 2 is a lower bound. Okay, for example, 0 is a lower bound of B, and 1 is a lower bound of B, and 1.3 is a lower bound, and 1.4 is a lower bound, and 1.4 yeah, this is a lower bound because it's less than square root of 2. So all these are a lower bound, and there are no upper bounds of this set. By the way, for the previous example, there are no lower bound for this set A. Now, the following lemma should be trivial. By the way, trivial in mathematics usually means obvious. Okay, so don't get confused. Trivial doesn't mean it's not important. It just means it's obvious. Okay. Anyway, so let S be a subset of real numbers, and A is a real number. Okay. Then A is not an upper bound if and only if. So if and only if, we sometimes write IFF. This means if and only if. If and only if there exists some x in S such that x is greater than A. Okay. This seems obvious, right? So if this is a subset and there is a x that is greater than A, then this A cannot be an upper bound of this S because there is a greater number in S than A. And similarly, A is not a lower bound of S if and only if there exists in S such that x is less than A. So this can be understood in a similar manner as this one, but in the opposite direction. So I don't give a proof of this, but it should be obvious. Okay, next we define another set of new concepts, that is bounded above or bounded below. Okay, and again, let S be a subset of real numbers. We say S is bounded above. So this means, by definition, S has an upper bound. Upper bound. Okay, so it simply means there is some real number, say alpha, that is greater than any of the elements of S. So that means S has an upper bound. If S has an upper bound, we say S is bounded above. Okay, similarly, we say S is bounded below. Below. So that means, by definition, S has a lower bound. Now, the following lemma should be also rather trivial. Okay, again, let S be a subset of real numbers, and let us define the following two sets. U of S, that is the set of all real numbers such that for all x in S, x is less than or equal to A. Okay, so this is set of A's. So that means this U of S is the set of all upper bounds of S. And similarly, we define the set of all lower bounds of S. So this is defined as this. X is greater than or equal to A. Okay. So if we define these two sets, the following holds. 1, S is bounded above. If and only if the set U of S is non-empty. Okay, and 2, S is bounded below. If and only if the set of lower bounds L of S is non-empty. So these are rather trivial, right? because it's not non-empty, S should be bounded above. If this is non-empty, S should be bounded below. And conversely, if S is bounded above, then there should be at least one upper bound. So the set of upper bounds should not be empty. And similarly, similar argument applies for the lower bounds. Okay. Okay, next we again define a set of new concepts that are supremum and infimum of a set. And infimum. Again, let's say S is a subset of real numbers. Then supremum of S, so which is written as SUP of S, so sup of S is the least element in the set of upper bounds of S. Okay, so let's say U of S is defined as this, so the set of upper bounds, and we take its minimum element, minimum of the set of upper bounds of S is called the supremum of S. Okay, so the least element, least upper bound. And similarly, infimum of S is written as INF. Inf of S is the maximum, the greatest lower bound. So that is the maximum of the set of lower bounds of S. So this is the greatest element, greatest element of L of S. That means greatest lower bound. Okay, so let's see a few concrete examples. Consider set A of real numbers that are less than or equal to 1. Okay, so on the number line, this represents the set, so 1, and everything below 1, including 1. Okay, so this is the set A. So any number greater than 1 can be an upper bound. So among those upper bounds, the least one is 1. So in this case, supremum of A is equal to 1. Okay. And in this case, this supremum belongs to A itself. Okay. This just happens to be the case for this set, but it's not always the case that supremum belongs to the set. Okay, second, again consider the set B of rational numbers such that that are less than, greater than or equal to square root of 2. Okay, so on the number line, let's say this is square root of 2. Then any number greater than or any rational number greater than or equal to that square root of 2 is this set B. Okay, so any number less than or equal to square root of 2, any real numbers, can be a lower bound of set B. And among them, the greatest lower bound, so that is the infimum of B, is square root of 2. Because square root of 2 is less than any of the rational numbers that are greater than square root of 2, right? Square root of 2 itself here. But this does not belong to B. Okay, in this case, the infimum doesn't belong to the set B. From this example, we can see that the least value of set B is not necessarily equal to the infimum of B. right? In fact, there are no such thing as the least element of B, because it is a set of rational numbers that are greater than square root of 2. This equality cannot hold because square root of 2 is not a rational number, but x must be a rational number. So there are always, for any element of B, there are always some rational number between that element and square root of 2. That's because the set of rational numbers is dense. Okay, so we can always find smaller rational numbers, but still they are greater than square root of 2. So there are no least minimum value of minimum element in B. So therefore the infimum of B cannot be an element of B itself. So here we define supremum and infimum a little bit rather informally, because we didn't exactly define the meaning of minimum or maximum here and here. So what do we exactly mean by minimum and maximum element of upper bounds or lower bounds? So here's a more formal definition of supremum and infimum. Okay, again, S is a subset of real numbers, and we say a real number is a supremum, the supremum actually, of S. So by definition, if this A satisfies the following two conditions, that is, for all elements in S, we have x is less than or equal to A. So this means A must be an upper bound of S. Okay, so first condition. And second condition, and if A prime is less than A, then that means there exists some element in S such that A prime is less than X. So what does this mean? If there is any element that is less than A, okay, then, so let's call it A prime, then this A prime cannot be an upper bound because there exists X that is greater than A prime. So if A prime is less than A prime cannot be an upper bound. So if these two conditions are satisfied, then we can say A is the supremum of S. This second condition essentially means that this A is the least upper bound, right? Because if anything is less than A, then it's not an upper bound anymore. So in that sense, A is the least upper bound. And the infimum can be defined in a similar manner. We say A is the infimum of S if it satisfies the following two conditions. That is, for all elements in S, we have X is greater than or equal to A. So this means A is a lower bound of S. And second, if A prime is greater than A, then that means there exists some element in S such that A prime is greater than X. So this means if any number is greater than A, let's call it A prime, then A prime cannot be a lower bound. So in that sense, this A is the greatest lower bound. And so if it's the greatest lower bound, then A is called the infimum of S. Okay, now let's prove some lemma about supremum and infimum. Okay, lemma. And suppose S and T are subsets of real numbers and T is a subset of S. Then, first, the supremum of S is greater than or equal to supremum of t. And second, infimum of S is less than or equal to infimum of t. You know, t is included in S. So in that sense, we can say t is smaller than S, but if that's the case, then supremum of S is greater than the supremum of t. And infimum of S is less than the infimum of t. Okay, so let's prove this. And actually, we prove only the first one, and the second one is left as an exercise. Okay, so let's say u of S and u of t are the sets of upper bounds of S and t, respectively. Okay, and let A be an element of u of S. So that means for all x in S, we have x is less than or equal to A, right? But t is a subset of S. So that means for all elements of t, we have x is less than or equal to A, right? So let's say this is S and this is t, okay, in the number line. Okay, so if A is an upper bound, then A is greater than any elements of S. So, and T is a subset of S, so A should be greater than any elements of T. So that's this and this. Okay, so what does that mean? Then that means A is also, wait a minute, not X. A is also an element of U of T. So A is also an upper bound of T. So from this assumption, we derived this conclusion. That means if A is an element of, is an upper bound of S, then A is also an upper bound of T. So that means the set of upper bounds of S is a subset of the set of upper bounds of T. Okay. So now, instead of considering S and T, consider the sets of upper bounds, U of S and U of T. So in this case, you know, this subset relation is opposite from this one. Okay, T was a subset of T, but the set of upper bounds of S is a subset of set of upper bounds of T. So if we consider the set of upper bounds, it looks like this. Okay, so if we take the least values of these, then the least value of U of S should be somewhere here. So consider this as a number line. And the set of the least value of the least upper bound of T is somewhere here. So that means this is less than this. Okay, so that means the minimum value of U of T is less than or equal to minimum value of U of S. So that means supremum of T is less than or equal to supremum of S. So that's what we are trying to prove. Now let's think about the meaning of real numbers being continuous, whereas rational numbers are not continuous. If we consider the set of irrational numbers, so we can obtain this set by removing all rational numbers from the set of real numbers. So if we consider the set of rational numbers on the real axis, then between each rational numbers, we have lots of irrational numbers in between, right? So in that sense, there are many spaces between rational numbers. But of course, if we consider all real numbers, then there are no such spaces. But what does that mean exactly? Consider this example. S is a set of real numbers such that when squared, that is less than 2. So basically, if you solve this inequality, we find x is between negative square root of 2 and square root of 2. So what is the supremum and infimum of this set? Supremum of this set is square root of 2. And infimum of this set is negative square root of 2. So both of them are real numbers. But if we consider the same problem within the set of rational numbers, then the supremum and infimum do not exist within the set of rational numbers. So that means we can adopt the following axiom. Okay, so here's an axiom of the continuity of real numbers. Continuity of real numbers. Okay, so if S is a subset of real numbers, then first, if S is bounded above, then the supremum of S is a real number. And second, if S is bounded below, then the infimum of S is a real number. Okay, so these seem trivial, but we cannot, these cannot hold if we only consider the set of rational numbers. Okay, these can hold only if we consider real numbers. And actually, we adopt these properties of real numbers as an axiom. So this is the big difference between real numbers and rational numbers. We know that the set of rational numbers and real numbers, they behave mostly in a similar manner. They are both fields with ordinary addition and multiplication. And we know that they are both dense. So between any numbers, there are always another number that are either real numbers or rational numbers. But there's this huge difference, that is the continuity of real numbers. Now, based on this axiom, let us prove Archimedes' principle. In a previous video, we actually introduced this principle as an axiom. But since now we have this axiom of continuity of real numbers, Archimedes' principle can be derived from this. Okay, Archimedes principle. So that is for any real numbers a and b, if a is positive, then there exists some natural number such that an is greater than b. So this is called Archimedes' principle. Okay, to prove this, we prove by contradiction. Okay, so to prove by contradiction, we first assume the negation of this statement. Okay, so the negation of this statement becomes like this. So for all AB, so this becomes there exists AB. So let's say suppose there exist AB that are real, and A is positive, and so negation of this for all natural numbers n, we have an, so negation of this is an is less than or equal to b. So suppose this holds. That is the negation of the claim here. Okay, then we have, so in particular, we have from here, for all n, we have n is less than or equal to b over a. So we can divide by a because a is assumed to be positive. Okay, so since this holds, a and b are given numbers, so it's a constant. So all natural numbers are less than b over a. So that means the set of natural number is bounded above. This already sounds strange, but that's the conclusion derived from our false assumption, okay? Bounded above. And because of the continuity axiom, the supremum of natural numbers exists. So supremum of n exists. And remember the meaning of supremum. That is the least upper bound. Okay, so that means so if s is a supremum of n, any number that is less than s cannot be an upper bound of n. Okay, for example, since s minus 1, for example, is less than s, so s minus 1 is not an upper bound. Upper bound of natural numbers. So what this implies is that there exists some natural number such that s minus 1 is less than m, right? Because otherwise s minus 1 can be an upper bound. So this holds, therefore s is less than m plus 1. But m plus 1 is a natural number. And it's a natural number greater than s, which is supposed to be the supremum of natural numbers. So this s should be greater than or equal to any natural numbers, but there is at least one natural number that is greater than the supremum, which is a contradiction. So m plus 1 is a natural number. This is a contradiction. So therefore, our assumption, this assumption, was wrong, false. Therefore, the claim holds. That is, Archimedes' principle holds. By the way, this one, an greater than b can be also expressed as a greater than b over n. It's the same thing. So this can be considered as a corollary to this theorem, lemma. Okay, let's see a simple example. Let A be a set of numbers of the form of 1 over n, where n is any natural number. And we want to show that the infimum of this set is 0. Okay, so how do we do that? First of all, for any natural number, n, 1 over n is greater than 0. So that's obvious. So 0 and any negative number are lower bounds. Bounds of this set A. Okay, so of course, if this was these are all lower bounds, then the greatest of all these numbers is 0. So we can say infimum of A is 0. But we need to also show that there are no positive numbers that are a lower bound of A. So let A be any positive number. Okay, and by Archimedes' principle, Archimedes principle, there exists some natural number n such that a is greater than 1 over n. Right? So in the original form, it was like a n greater than b, but in this case, b is 1 and a is any positive real number. And so we can express the same thing as this, a greater than 1 over n. So what this implies is that a is not a lower bound, because it's greater than some of the elements of A. So, but A was arbitrary, so no positive real number can be lower bound of A. So that means the infimum of A, the lower bounds are 0 and negative numbers. So the greatest of all these numbers is 0. So therefore, the infimum of A is 0. And here's another example. Let A and B be any real numbers. And suppose if for any positive epsilon, if we have A minus B, its modulus is less than epsilon, then we have A is actually equal to B. Okay, so let's prove this. Let's prove this by contradiction. Okay, suppose, so the conclusion is this. So suppose A is not equal to B. Then the absolute value of A minus B is greater than 0. So by Archimedes principle, there exists some natural number such that this positive number is greater than 1 over n. So, however, our assumption is this. For any positive number, real number, this modulus is less than that positive number. But here, it doesn't hold. It's opposite. It's not less than, but it's greater than. So this is a contradiction. This contradicts the assumption. So this was wrong, and A must be equal to B, and we are done. As a consequence of Archimedes' principle, or the continuity of real numbers, we can show that the set of rational numbers is dense. That means for any open interval AB, so A and B are any real numbers where A is less than B, we can always find at least one rational number in this open interval. We can always find. Okay, and as a result of this denseness, we have the following interesting facts. That is, for any real number alpha, and for any positive epsilon, there exists some rational number such that alpha minus A is less than epsilon. Okay, so this means however small this epsilon is, as far as epsilon is positive, we can always find a rational number that is close enough to any real number alpha. So this means we can always approximate any real number by some rational number. Okay, so this epsilon is a kind of limit of the precision. So this epsilon can be very small. So however small this epsilon is, we can always find a rational number that is close enough to alpha. So this fact is very easy to prove from the denseness of rational numbers. So we consider an interval alpha minus epsilon and alpha plus epsilon. So since epsilon is positive, strictly positive, this is non-empty. Okay, so alpha minus epsilon is different from strictly less than alpha plus epsilon. Okay, but from the denseness of rational numbers, there exist some rational numbers such that alpha minus epsilon is less than a, less than alpha plus epsilon. So this means this a minus alpha and less than epsilon. So this means a minus alpha is less than epsilon. And of course, we can swap the sign inside a modulus sign. So we have this. And you should try some experiments with real numbers. For example, square root of 2. Let's approximate this by some rational numbers within this precision, 0.01. So since square root of 2 is something like 1.42 3 and so on. So for example, a is equal to, if we take a equal to 1.42, then the difference is less than 0.0013. So this is precise enough within this precision up to the second decimal. And even if we want to increase the precision by adding more zeros here, like we can just extend this approximation by something like this, and so on. But this is still a rational number. So we can continue this forever as long as we are satisfied. And let's take pi. So consider approximating pi by some rational number. So if this precision is something like 0.001, then a equal to 3.14 isn't enough, because pi is something like 3.141592 and so on. So if you take the difference is greater than 0.001. But if we loosen a little bit the limit of this precision, then this is fine within this precision. But of course, if you want more precision, then we can just pick up to, for example, this digits. Okay, so that's all for this video. See you later.